Hi everybody, thanks for coming. I know it's a 9 a.m. talk on the first day, so thanks for making it. I'm going to be talking about extensions, in particular how to push the boundaries of what extensions can do and how they can do that with extensions. My name is Yurii and I'm with Omnigress. At Omnigress, we do a couple of interesting things. Basically, we create a whole data-aware platform where you can run your applications right within Postgres and do some other interesting things like query acceleration and database guarding, sort of interesting things that create the entire application environment. And the whole idea is that with Omnigress, and you'll see why we care about extensions so much, is that we see Postgres as not just a database. We see this as a platform that can help creating data native applications, or what we call data-aware. So to that end, what we do with our users and customers, we run application logic right inside of the database. We serve things like HTTP right from within Postgres, and we get amazing results. For example, we see up to 5x performance and latency improvements by not having a separate application server. And we augment Postgres behavior significantly, so that basically gets into hooks and query planning, query execution. So for all of these reasons, we really need to be very deep in Postgres, and extensions is a way to do that. Our general approach is that we're not forking Postgres. That's very important to us because we want people to take vanilla Postgres, drop in our extensions, and be able to do what they want to do. However, for the purposes of this presentation, some of the ideas will actually be requiring in the future not forking Postgres, but contributing to Postgres some changes that unfortunately are nearly impossible to do today with extensions. So moving on from that, we've built a lot of extensions. I think right now about 15 extensions total. But here is an example of a few that particularly relate to building extensions. So one is called Omni, and that's essentially an extension for extensions. It doesn't really do anything useful to the user per se, but it really helps extensions. And it started with an idea, hey, can we have better APIs for extensions? And can we actually avoid restarting Postgres every time we add shared preload library extension type of deal? Omni Manifest helps installing extensions, especially when you have a lot of dependencies between them, or if you use a lot of extensions. And I'll show a little bit more on that later. Omni VFS, it's an extension that allows you to abstract different type of file system type of sources, like your local file system or S3 bucket or Git repository as a file system, so you can deliver your code to the database in an abstract manner. And OmniPython basically is an improved experience over PL Python, and one of the most important things about it, it automatically manages your dependencies. With PL Python, you typically need to bring dependencies manually, and nobody wants to do that. OmniPython just solves that, automatically deploys your dependencies wherever you need that. So I'll start with the most important topic for this whole discussion. And we've actually had an amazing discussion about it yesterday at the Extension Summit. And that is, what is Postgres API? And turns out even core developers are not always sure what's public API and what's not. And there's no clear definition of what extension APIs are supposed to use and what they're not supposed to use. So there's essentially a delineation that is not very well defined between green APIs, as in they're blessed and you can use them. Gray APIs, as in like exercise caution, there are certain things you have to be aware of. And outright red APIs, basically do not use them. This is like a really, really bad idea. Although heads up, some of us do use red APIs anyway. Like if we can figure out a narrow use case where they're useful and we're reasonably sure that they will be safe in this particular context, there's still often at times a need to use them. But what's important about this, and what we figured out yesterday, is it's important to actually start defining these lists in writing, so we can communicate between extension developers and core developers. What do we use? What do we rely on? And what kind of needs do we have? But it's an important topic overall for extensions. And there's another interesting part of the API conversation is if you look into how extension API is in Postgres, it only tracks the major version of Postgres you're compiling against. Is this a problem or not? I've received different opinions before on this. Some people said major is fine. Some people said you should actually track minor as well. So I set out to do an experiment and just do a little bit of git diffing between versions. Turns out there are some interesting changes. So for example, between some versions in release 16, some data structures receive new fields. So if you build against, say, 16.2, run on 16.0, that new field will be garbage, effectively. You can't rely on that. There are new APIs, and they appear in different ways. So you will have, say, inline functions, macros, or actually definitions of symbols that you think will be there, but they actually won't be there. So you'll actually fail to load the extension. So you have to be aware of that. There are even more interesting aspects, like, for example, some inline functions change their behavior between minor versions. So this one in particular, I believe, fixes a bug. So if you compile against an earlier version and then run on an older version, you're bringing the bug from the previous version of Postgres into your extension. So lots of interesting things. Generally speaking, I think you are kind of okay unless you go really deep into some really dark corners of Postgres, but you never know. You might run into it without just knowing it. And you have to remember that Postgres will only check the major version. So it will error out if you're trying to load extension for 15 on 16. That's clear. But otherwise, it will not check that for you. With the Omni extension that we have, we actually do check for minor version and issue a warning right now, just saying, hey, this is not the same minor. Like, tread carefully. So now let's get closer to extensions themselves. There are two types of extensions, effectively. One is actual extensions, so the ones that you create by doing the create extension command. And they're scoped by database. So basically, whenever you create extension, it's only in that particular database. You have to have control files, SQL files, update path files with them. And for running the native code part, it's essentially relying on language C, like for create function language C. Extensions do not provide this themselves, but it's the create function functionality and DL open effectively provide you access to native libraries. But the most important part about extensions is that they're user-driven. They're not really acting on their own sort of volition. The user has to install it, and the user has to call into functions, use the tables provided there, use the types. So it's kind of inert in a sense, for the most part at least. And I'll run through a couple of issues that extension developers such as ourselves find interesting or problematic. So one is dependencies. There's a very clear problem with dependencies that we have on our hands right now. The dependencies are unversioned whatsoever. So you say, I depend on extension ABC, and that's it. Version 1, version 2, version 3, who knows? Some version. And that's not a great expectation to have, because it might work, might not work, might blow up in a terrible way. You just have no control over that. And even if we had version dependencies, we can't really resolve conflicts. If one extension depends on one version of the other extension and the other one depends on the different version, Postgres does not have an ability to install two versions of the same extension in the same database, and that's problematic. And here's my first suggestion that does require contributing to Postgres. Can we reconsider the idea of nested schemas? So we can actually borrow from programming languages ecosystems like Python, for example, where they have virtual env. So where you can create an environment with schemas inside and set your search path in there, so that depending on which part of the application you're working with, you can create isolated schemas with sub-schemas with those extensions inside. So that would definitely require patching Postgres. The good news, however, with dependencies, there are some solutions that we can apply today without changing anything. So basically what you can do is something like that. You can insert a little bit of PGConf code or abstract it to SQL code in some way, where you actually check what is the version of a particular extension I'm dependent on. And if it's the wrong one, we'll raise an exception and that extension will never get installed. So you can see just right over there, if the version isn't correct, it's unsupported, raise exception, we're done. So we'll never get it installed. So it solves the problem and allows you to test for more than just a version. You can test anything about the shape of that extension. Do we have a table? Do we have a function of a certain shape in that extension? So you can do whatever test you want. It's kind of nice. But what's not nice about it, it's not introspectable. So you cannot actually see what that extension wants. It will only just blow up in your face, as opposed to having a format that describes, I want this particular version of extension, I want this and that. However, even taken from there, we can still do something. We can use for example, the comment system, and we can actually store some dependency information in our schema. And provided we have a way to interpret it, say, for example, in the future with the Omni extension, at the end of the installation of the extension, if we override that particular utility hook, we can say, hey, that's not the right combination of dependencies that you had. Let's bail here. You will not be able to install. So this way, there's a way to introspect to a degree. It's still not perfect, but it's just an idea what we can do today as well. Furthermore, as extensions grow, you need more extensions, and these extensions start dependent on other extensions. And the system we have today is not really conducive to that. So every time you need to create or update extensions, you have to do this essentially manually. So you have to figure out which extensions you need to install, and for those you need to issue create extension name, etc. And then for those that you're upgrading, you need a completely different command. You need to alter that extension and update it. So to that end, we developed a pure PGConf extension called Omni Manifest. So you can install it anywhere, like Amazon RDS if you want, where you feed a simple line there like this, saying which extension I want and which dependencies it has. And it will prepare and execute a plan in the correct order. So you can have actually more extensions than just one. This example just has one main dependency. And it will figure out basically the graph of installation and just run through it and error out if something happens. So this way you only issue one command at a time for updating the entire system. And you can also use essentially tabled information to do that. Whereas with create extension, you're hard coding the values essentially in every command. Here, you can actually put all this information in some table and select from that table and feed into this function, the Omni Manifest install function, feed whatever you want into that function and receive a report. So for example, these two extensions were kept at whatever versions they were, and that one was updated. So really helps with working with complex installations. The related part here is managing migrations. So I think developers of especially popular extensions like Postgres, they have a problem of managing complex deployments where you have the main line of development, but then you have backports and et cetera, et cetera. You have to be able to provide migrations for all paths that lead to, through upgrade sort of trajectories. And that just puts a lot of burden on developers. And there's still no great solution to this, but there are conversations on the mailing list how we can improve that. But what's important to consider here is, what do extensions typically use migrations for? And oftentimes this is obviously functions, views that depend on those functions, new data types and everything related to them, and to a lesser extent data. Some extensions do bring some data to be able to use it. And I wanted to focus on functions. There are actually different types of functions. So one is self-sufficient functions like SQL functions or PGConf functions that essentially the code is right there in pgproc catalog, and there's nothing else required to run them. So they have no problem. They're kind of the best case of application of PGProc that we have right now. There are semi-self-sufficient functions. So they still have the source code in the database. For example, it could be a Python function in Python 3u, but they require certain Python libraries, because that's oftentimes the value of Python. Not the language itself, nothing wrong with it, but the ecosystem is really fantastic there with all the libraries. So what do you do? Typically, people have to figure out yet another part of their DevOps. How do we bring the libraries to the server where we run all of this stuff? Or how do we bring native libraries? Like if we have some dependencies, like how do we ensure that they get installed correctly and linked correctly to our extension? So for Python, in our experience, what we've done is with OmniSchema and OmniPython extensions, we automatically provision the dependencies that are defined in a requirements.txt file. So basically just a file that describes what you need. And whenever you bring these functions with these requirements, it will just install it automatically, whether that's your development machine or your CI/CD or your production. So just automatically using OmniVFS, schema and Python is kind of conglomerate of different extensions. And for native, we have some suggestions to extension developers what to do about that, about native dependencies, such as, let's say you want OpenSSL as a dependency of your extension. One is static linking. Of course, it increases the size of your extension, but then you don't have to worry about it. It's just always the correct version of that dependency right with your extension. The other one that we had a good success with is RPath. And it's a lesser known thing that allows you to specify in your SO file that you will be looking for a library not in any system path for libraries, but in the same directory or adjacent directory. So you can bring two files together and it will actually link to a correct file and will not use the system file for that. So that's kind of convenient. And there are referenced functions. So those are kind of the most tricky ones. Those are the ones that don't have their source code in the catalog. Oftentimes they do not have source code whatsoever in your production because they're compiled. They're somewhere in the Git repo, but not on your system. And they essentially just refer to the file and the symbol in that file. That's basically the case for all the native extensions. And there are some significant problems with that. And one, we observed it for ourselves. I think we also saw this in timescale, for example, extensions, where whenever you're changing from one name of the file for extension to another, basically, if the file name changes and you do not update every single function, then you have to create or replace every function to update where they point to. Otherwise, they will keep pointing to the old versions of the file. Therefore, you think you're in a new version of extension, but your functions are actually pointing to the old ones. And I believe, like with timescale, they also solved this problem. We solved it slightly differently, but it's an important problem to realize because most people are actually unaware of this problem. They think PGProc always points to the right thing, but it doesn't. In our case, what we do with Omni extension, we basically, every time you update an extension, we go back to PGProc, check the references, and if we were upgrading, we update all the references automatically. So basically figuring out what happened and applying that change. But it actually poses an interesting question here. Are we going through the layers of abstraction too quickly here with Postgres, where we only have the reference to symbol in ProSRC and to the file in ProBin? Should we maybe refer to an extension instead? So instead of referring to a file, maybe we should consider referring to an extension that we installed. So this way, whenever we update it, considering we still can only install only a single version of the extension at a time, we just know that it's going to be from the native files in that particular extension and not a particular file that may be already an old version of the extension. So that's an interesting thing, and that definitely would require, again, patching Postgres. That's not something we can easily do outside of it. And another idea that came to my mind at some point, I was at some point contributing to PGRX, and what they do a lot is they contain the schema for their extension in their SO files. but they use it to essentially produce the migration scripts afterwards and package them the traditional way. But what if Postgres itself had an ability to extract the function signatures, perhaps type signatures, out of the SO file as a source of truth, instead of relying on your migration scripts to put them into say, PGProc and other catalogs? Can we actually get it from the native code altogether? Again, definitely would require patching Postgres, but an idea nevertheless. The next problem that we have is a nasty one, unfortunately, and that's relocatability. A lot of extensions just hard code the schema name because it's kind of the easiest way to cope with reality. And the other part that they often have to do is either use their types and other references by name, or do OID retrieval. Basically, if we don't have the OID for a particular object like our type or something like that, we need to retrieve it and hope it will not change, and then cache it somehow. Or not cache it, but then incur the penalty of retrieving it every single time you need it, which can be prohibitive. And the suggestion here going forward is, can we use hooks to actually communicate which schema this extension is in, what are the OIDs of your dependent objects directly to the extension. So whenever it changes, we can track that with a hook. There's a callback or something to that end in the extension that will receive the updated information. So you're never really questioning yourself, is this stale information about the OID? Is this stale information about the schema name? You just know that's the latest one, within the transaction in the backend that you're working with. Yep, and yet another one is fragility. Basically, extensions cannot expect that the schema and the objects that they have created will be intact. Theoretically, it's not impossible for the administrator to just change it underneath, for good or bad reasons. But that means we don't really know what, we deployed this, but now it's out of our hands, that's in administrator hands. And if administrator does something by mistake or otherwise not realizing how it can affect the extension, we're in deep water there. The best case scenario, you'll just start erroring out. But depending on how you built your assumptions in your code, you might even segfold, theoretically at least. So that's not great. And to this end, we have been doing some experimental work. It's not merged in yet at all, but it's a very similar idea with hooks. Hooking in, we can actually say, hey, we're not going to be able to change anything in the objects that you deployed as part of the extension unless you are doing alter extension update, basically prohibiting everybody else from touching it. So it's kind of what we call sealing the extension, so that basically nobody can make a mistake changing it unless they're upgrading it. Now, yet another topic. And I know it's compressed, but it's a whole big space. Background workers, particularly with extensions. As I said, extensions are user-driven, and that's a problem. While you can sort of call a function from within your extension in your upgrade script or your initial migration script, the problem with that is if you start a background worker out of that, there's no guarantee that at that time your migration script will be committed and visible to other backends. So you start your background worker expecting that there is already a complete schema for your extension there, but oftentimes it won't be because it's too fast and we haven't committed it yet, or we have committed but it's not visible to other backends. So you essentially can just wait and retry, like, is it there yet? Is it there yet? But that's error prone. That's not great. That's not a great experience at all. And second problem is even bigger. It's not fixable at all. And that is, if you install this as an extension, whenever you restart Postgres, there's no way to start that background worker again, because it's user driven. So basically it's gone. You have to manually restart it. So with that in mind, in the Omni extension, we came up with a essentially interface that allows you to register background workers, regardless whether it's a startup time or installation time. It will automatically bring things up and running at the right time. So the most important call there is basically request background worker start, and it's very similar to regular API. But what's important there is this line. It's timing. You're telling Omni when to start the background worker. And this one in particular, after commit, says only when the transaction we're calling in has been committed and visible to other, like the changes are visible to other backends, only then start the background worker. So this way you can guarantee that when you start the worker, the schema is there, everything's ready. And here we're using a mechanism that I will be describing in the next slide. It's called atomic switchboard. It basically allows you to do leader election. So it kind of looks like this. If you ask ChatGPT, basically, basically what it means, you have a bank of bits. Right now it's just 64 bits, 64 switches, and you can turn them on and off automatically in a single atomic operation, saying I want to turn on these 5 switches. I mean, I don't know when you want 5 switches, but 1 or 2 are usually the case. And what it helps you with, it will atomically do that, so multiple backends can try doing this at the same time. But as a result, it will tell you which switches you changed and which switches were already changed by somebody else. So this way you can know that you were the ones who flipped the switch either to 1 or to 0 and take the action. So in a sense, it becomes a form of leader election. So you can, for example, if you go back to the original code here it says basically if we were the ones to switch the master worker start switch, then we are the ones starting it. Otherwise, nobody else will start. So basically this prevents this race condition when multiple backends will try to start the background work at the same time. Let's go further. Hooks. Now finally we're getting to the really big meaty part of Postgres. So they're absolutely powerful. Obviously you can do a lot by augmenting hooks just about anywhere. We still don't have enough of them, as everybody's in the extension community is saying. But even the ones that we have, they have problems. First of all, again, they cannot be provisioned by extensions themselves. It's typically the shared per-loaded or session per-loaded libraries. And there's no good way to introspect which hooks you have, remove them, or profile them, which ones are taking the most time. You can't really do that. And so what we have experimented with and had good success with is create a system where we supplement the extension system that Postgres has and replace it with a different hook system, where the names and signatures are very similar, but first of all, they're not using the same execution model, because in Postgres hook system, you have to save the previous hook and call it at the end of your version of the hook. And so that creates a cascade where, first of all, obviously you're growing the stack, which is not always the best idea. But also, upon removal, you can't really tell what was before that because that's a private knowledge of a particular hook. What we have created is a linear execution model where it's essentially an array of hooks. They have an order. They don't know about each other. They just tell what's the result of my execution. They can save a little bit of state, and they can say, hey, terminate the whole thing or just continue. And so we continue running them. So that allows us to see a lot of things. And what's very interesting, they're transactionally aware. And I'll show something here. So in this particular case, there's an extension that it's just a test extension for the unit tests that we have. In the first one, we're introspecting which hooks we have with Omnitest. And because we didn't install it yet, there's nothing. There's zero hooks that it has installed. But then we're starting a transaction, creating the extension, and doing the same query. And you can see it has 3 hooks, and they're position 1 because they're new hooks. Nobody else used them. But then we roll back, and we don't have these hooks anymore. So you can essentially create a transaction, install an extension that it will bring its own hooks. You can test it out. You don't like it, roll back. No other backend is affected. It's just completely, try and see how it works. It's really an amazing mechanism compared to what we have right now in terms of correctness and experimentation and tests, all of that. So moving on to the general types of extensions we have. The other one is library. They're simpler in a sense. You have to change Postgres config to load them. So you essentially have to touch either shared per load libraries or session per load libraries to load them. and they're cluster scoped as opposed to database scoped. And they're using DLOpen, of course, for all of that. And cluster scoping is kind of problematic. Oftentimes, these extensions bring really important functionality, but the hooks and whatever else they do, they apply to everything in your cluster. And it's not always the case that you want that. And so the question is, can I have them only for my database that I want them in? And the other one is obviously the change downtime. So whenever you need a new extension, or you want to remove an extension, or you want to update an extension, you have to restart Postgres every single time for those. It's kind of problematic. So the question that we ask ourselves is, can we have the best of both? Both the extensions and the library extensions. And this is why we created this Omni library, or extension rather, that I've been referring to. Basically, the hope behind it, it's the last one that you need to add to your shared parallel libraries and never touch it again. Just that. And we use it in OmniGress to power like Omni HTTPD and other things, and we keep experimenting on it. And we typically try to keep it very small. It basically introduces a new sort of a magic signature to it and some information like name, version, identity. And it has only 2 callbacks, the init callback and de-init callback. That's all it has. These allow you to set up a particular backend and deinitialize that particular backend when things sort of go out of scope. And I'll run through a couple of things that it offers right now, in addition to what you've seen already. So one is the Grand Unified Configuration Variables. I personally had a lot of interesting small problems with them. So one is the API is hard to comprehend. They usually have like about 10 parameters each, and it's different functions for every single type. And the other one was the redeclaration. When you have different backends competing for who is going to define the configuration variable, you have to be very careful, because if it's already defined, Postgres will error out saying it's already defined, and there's no great way to check it. There are some janky ways to check whether that variable exists, but then you have an even harder way to get to the pointer that will give you the value of that variable. That's kind of problematic. So what we did there is kind of twofold here. One is completely change the API, make it uniform, and make it actually very readable, because it's using the initializer syntax. So you always know what we're talking about. This is a description. This is the long description. This is the type, the context. So you always can understand the meaning of these parameters. And that same structure will receive the pointer. So that's the other important part, to the latest value of the variable. So whenever it's happening, you can read it from the very same structure. The other one is shared memory. So a lot of people who develop extensions, they end up using shared memory to, say, communicate with background workers or something like that. However, not everybody is aware that of DSM, for example, has some hard limits. This particular one up there, it's basically 64 fixed slots and 5 slots per backend. And that's all you can have. And you have to be extremely careful about whether you're attaching or detaching from your memory segments, because you can easily run into these limits if you go above the limit. And obviously the DSM, DSA APIs themselves are not the most user-friendly ones or developer-friendly. And in particular, what we found, there is not really an API for idempotent DSM attachment. So when you attach to a segment, if you haven't attached to it, it works beautifully. If you have previously attached to it, it'll just error out. So you can't really reattach. So you have to track what you attach to and kind of connect that back. That's what we did. So that is not great. So we provided an API that disconnects you from DSM API. It just gives you a direct API to work with shared memory. And part of the hope there that soon enough we'll actually break away from using DSM whatsoever, because it's just an operating system facility in the end. Just provide a way to work with shared memory and share the information between the backends. But it's also module scoped, so every module has its own sort of namespace, so you're not clashing with other extensions. Your allocations are named, and that's oftentimes very important because it allows you to do only once allocation. So multiple backends can go and try to get allocation of a particular size for a particular name, but only one will do the actual allocation. So that's very important, of course. And it has all the naming, sizing, and callback information, so you can act when it's registered. And also what's important about this, it's completely introspectable. So using Omni extension, you can actually ask, what are my allocations? What are the sizes? How many of backends are actually using it by looking at reference counters? And what's the size and what's the extension doing that? So you can see all of this right away just in a view. So I think we're going still doing pretty good on time. We have about 15 minutes, but just a general reflection on what we've talked about so far. So one is, what is extension API and what should it be? How do we communicate extensions requirements such as dependencies and version dependencies? How can we generally improve the installation experience? And should we even consider the situation that we're in right now with extensions and libraries, that these are two slightly different things, that maybe we need a new version of the whole thing, call it something else, like a plugin or something like that, where we merge the good sides of both, get rid of the bad sides of both, and actually have a unified interface that allows Postgres to be more extension first even, so it's really truly extendable, as opposed to what it is today, where it's almost accidentally extensible. I've also covered Omni as a playground for really fast iteration and experimentation, because it does not require working with the core development team to get any sort of functionality, but we can quickly iterate and find what are the APIs that we need, how should they look like. So the invitation here for all the extension developers to join us in this discovery and see, what do we all imagine as our future API that we want, and some of it may remain as an external piece to Postgres, and some of it may make, all the way to Postgres over time. Now it's time for questions and arguments. So the question, I'll repeat for recording. The question is, because, for example, Fedora packaging guidelines suggest don't use relocatability whatsoever. And the question is, do people actually use it? From my, again, personal perspective and what my angle of vision, people generally don't use it, but for different reasons. In a sense, most of extension developers don't want to do this because it's difficult and it's hard. All the problems that are listed, like how do I actually know the OIDs? How do I actually know the name of the schema? How do I make that performant at the same time? So it's a problem that is kind of circular. We need to break it somewhere. The question is where, but it feels like if we actually solve the problem of actual relocatability, maybe we can get to packaging and let them reassess eventually, saying that we get this and these benefits from this. So for example, we can support scenarios where we can put different versions of the same extension in different schemas. So it's a longer term play, and schema is just only part of it. Things like, for example, being able to retrieve the OIDs of the types that you use is also very important, and ensuring that you always get the correct OID there over time. So even if things change, you're not caching the old value of OID. So kind of self-discovery of the schema.
Some of the challenges with making it work correctly.
Yeah.
Do you think it's needed though?
I think it is. Like we're using OID discovery is really useful and going to be. Yeah, I find this to be a part of the relocatability. Schema is one, OID discovery is another one. I do think it's useful because otherwise we have an artificial limitation about where things can be and how they self-discover themselves. That's just not conducive to future growth, right? So the more extensions we get, the more ideas we get in the space, the harder it is to innovate, essentially. So I find that an impediment. Maybe not for today exactly, but for, say, the day after today, and after, I think it will be more of a problem. Yeah, so the question was basically there are different types of hooks available throughout Postgres, especially a notable example of PGConf hooks that are not really cooperative to other sort of models of hooks. I would add actually transaction callbacks are kind of a good example of that. They're also different. Yes, I do believe that hooks should be uniform, and we need to have a very uniform. There's no physical reason in reality there why they should be different. And the more confusing they are, the more incompatible they are, the more, again, we're impeding the ability of extension developers to innovate. So 100% agree with that. Amazing question. So the question is, besides the hooks themselves, is there an intent to integrate like probes, like dtrace or similar probes into it? I think I would have a twofold answer to that. So one is, I want to do a minimalistic probing of hooks themselves, as in just basically collect sampling of their timing, and obviously being able to turn that on and off, depending, because you don't want always collect sampling in production, just sometimes. But so basically what I'm saying is there's definitely a need for some primitive tracing in Postgres itself, or the extended version of it, or say Omni extension. But I think the probes as an operating system level probes are also an interesting part to this. I haven't really spent any time on that, but it's something on the back of my mind. Yes, like it's kind of the more, if you wish, enterprise-grade way of assessing, the operational properties of your software. So that, especially debugging problems that are difficult to debug, people oftentimes run into, say, lock problems, especially when you start involving extensions and they do their own locking. Who knows what's happening, right? So tracing of all kinds is important. So going forward, I think it will be a very big part of it. Okay. Great question as well. So to repeat it, how does Omni handle the case when there's multiple connections to the database and we're installing hooks and they can be different and they're in their own transactional context and all that? The important part here is basically you have to think about the execution model of Postgres. It's all process per backend. Backend has its own hooks. Like hooks are not per Postgres. Hooks are essentially per backend. So basically, when you install a hook, it first installs in the backend. While we're still in the transaction, it's just completely local to the transaction. And that's why we have the opportunity to do rollbacks. And when it gets committed, there's certain mechanisms in Omni that the easiest way to describe that. So basically, when your other backends sort of catch up with like the next sort of cycle, they essentially are able to see that there was an installation of hooks elsewhere, so they just bring them into their own respective backends, if that helps. So we start with the local backend and then kind of grow out of there. So they're always local first, and that's why rollback works, because it's just local to that particular backend.
Okay, so I guess when backend starts, there's some sort of initialization, and then somehow it's not hooked to your logic to swap things.
Yeah, so like Omni is responsible for the entirety of your backend pool, right? The entire cluster will eventually receive this at the right sort of transaction time. So basically, when it's actually committed, then it propagates. It's a little bit intricate and complicated, but the hope is to do it sort of once, really vetted that it really does work, and then just carry on. And so far, it works really well.
Cool.
Yeah. Any other questions? Okay, yeah, so the question is, like I showed the slide where I was making suggestions about using some form of metadata inside of the extension to communicate what extension needs or wants or provides. And the question is whether that's a sort of a proposal, what we should do.
No, I knew you would propose using the comment, but are you proposing we need to do something, or are you just stating the case, saying, look, we need to control new architecture? A bite-sized thing, or do you want?
I'm making a proposal that we need to look into how extensions define their needs and what they provide. And actually, in that slide, I didn't really mention this, but I think it's a good time to bring this up. There are other things that extensions can communicate. So, for example, if you look at our Omni HTTPD extension, that is, the web server. How do we communicate to, say, a service provider such as, a managed database provider, that we're exposing a port, say, 8080, and that's HTTP, so that they can actually route traffic to it? How do we expose that? So if we have this metadata piece of the extension that says, hey, we needed this and this version of dependencies. We're also exposing this in that port. This is also how you can query other things that helps the outer environment, such as the managed database provider, to understand the needs and wants and the effects of the extension in a formalized way. So I'm proposing to start working towards that. Whether that's going to be comment or something else, I don't really know. But I think there should be a way to explain the formalizable parameters of the parameters and readouts, so to speak, of the extension, if that makes sense. So the question is, are we essentially adding an ability to do hot loading of extensions? Yes, with Omni, that's kind of the dream. Since you insert Omni as kind of your last or the only entry to shared preloaded libraries, it allows you to add new library-like extensions, unload them, update them at runtime. So the hope is you should never restart Postgres unless you're upgrading. I mean, hopefully in the future we don't even need to do that. But the idea, yes, it's hot code reloading. It's important because you don't want to stop the world, especially in the model that we talk a lot about, the ability to run the business logic inside of the database. We don't want to stop all of that to just update an extension. That kind of goes contrary to our beliefs. And I had many years experience in the Erlang community back in the days, and there's a huge virtue of being able to update your services as you run without stopping them. So I've learned a lot there, and I'm trying to get some of those sort of ethos, maybe not the methods exactly, but also some ideas how to implement that and what are the corner cases there. I'm still relearning from my past experiences there. Great question. So the question is, how do we deliver, say, our extensions and their dependencies in sort of in a binary format? Like, are we using any particular registries? And also, whether the functionality like hot code reloads apply to any other extensions or only Omni extensions. So I'll start with a simpler one. The hot code reload functionality only applies to Omni-powered extensions, so they have to be hooked into this system of Omni. So that's the only way to benefit from it right now, at least. We haven't really thought how we can do that for extensions that essentially do not cooperate with this sort of API shape. Can't think of a good way, because basically we're exposing APIs that allows them to do certain things. The other part with regards to how we ship them, we have our own smaller ways, we have our own sort of index registry where you just download a file and you just unpack it and just install it. It's kind of the simple way. And we're talking with other registries about including Omnigress components there. My personal opinion is that at least for some time, we'll still have a competition in different ways of delivering, through different registries. So we already have trunk, we have some interesting work from Postgres guys, coming up, something interesting there as well, and a few others. And what that probably means for a lot of extension developers is that, and ourselves as well, that you kind of have to, if you want to expose your extensions to the widest audience possible, you need to be everywhere. And that's a little bit unfortunate because it's more work. So the hope that eventually over a couple of years, we will consolidate on a more or less main way to do that. But I personally can't see a clear answer to that question right now. There's a pros and cons with every approach, and we'll see how it will play out. But for now, we'll try to support as many as we can, starting from just our own hand-rolled kind of implementation of that. Just if you're not using anything, you might as well just use our approach. But then get into other registries and let them run. And the conversations that we started having recently is actually about how do we communicate the needs and the exposures of extensions, such as listening to particular ports, to to users of those extensions. That's that's an important part also when it comes to metadata in the registry and how the users of those registries, such as managed database providers, will be cooperating with that. So it's a whole journey of discovering that. Yeah. Any other questions? Yes. Yeah, so the question is, do we deal with referenced functions in any way when they're potentially referenced in the old version of the file? There was a slide actually talking about exactly that, but I can just talk about it. Basically, the problem that we've noticed is when you update an extension and the name of the file is different, and there's a good reason for it to be different. You don't want to overwrite a file in production, an SO file, because oftentimes it will be cached, which is also not great. You are not getting the new functionality because Postgres will cache it or operating system will cache it, and you just don't know what's going to happen. And even if it didn't cache, changing the file in runtime is just a terrible idea, right? So obviously yeah, boom, So basically, the way we deal with this, every new version of the extension, for native files, you get a differently named file. And so when you do that, and when I assume you don't need to do any migration from there, that's a problem because all your create functions that you referenced, the original file, they will still point to the old file. And so even though you did not add any new functions or didn't change any signatures whatsoever, they will still point to the old version of the extension, that is the old file. And that is a big problem. So what Omni does is it has a hook in alter extension update. And it sees, okay, we actually did an update from this version to that version. And it just goes through the PGProc catalog, finds all the functions referencing the old file, and just rewrite in every tuple there to have the new file there at the end of that sort of command. So by the time it's done, it's just automatically there. So the question is, how do we deal with cache invalidations there? We invalidate actually, I think, one PGProc cache there. But it's an important topic there. We found that there are actually bigger problems with cache invalidation when it comes to functions. So for example, you can open 2 sessions with Postgres, call function in one session, then drop that function in another session, and it will still be callable. Like even today, without any shenanigans whatsoever, just vanilla Postgres, there's a problem that dropped function doesn't mean it's not impossible to call it. It is actually possible to call it, even though it's no longer in the catalog. I think it's a larger problem that probably needs to be addressed in Postgres itself. So the question is, do we require sort of restart of the backend to load a new function, or?
If you're referencing 2 different shared libraries and providing essentially the same functionality, do you load both of them, or?
Yeah, when you install the first version, right? The first version gets loaded and provisioned in PGProc just as it would normally do, and then when you have a new one, Postgres will load it, but we'll also load that library, and discover everything that's necessary there. And when we see that your update is not matching the version of the file, we'll just update the file there. But they're both loaded, as in DL open loaded, but the PGProc tuples will refer to the correct version at the end, like at the end of the alter extension update, because it's just a hook that sits there and controls that particular problem. Because other
Version functions as well.
Not within a file.
Okay, so how won't you load like 2 symbols that are the same?
But these are 2 different files and the particular two different handles. So like we're not conflating 2 versions of the same module. Does it make sense?
Shared libraries can actually export the same symbol by name, but they don't conflict.
Okay, but you need to keep track of that.
Not for shared libraries. Their own namespaces are completely, separate. You look them up by strings, basically. So just this, and you get a pointer in the back, from that. So the question is, how do we unload hooks and maybe Omni modules in general? So I'll split it in 2. So with hooks, basically, whenever you remove a hook, by way of, for example, not committing to a particular extension or drop in the extension. Because we don't have a chain of hooks like we do in Postgres, right? We have an array of hooks. It's completely introspectable array just pointing to, here's the stuff, right? Like we'll call this, we'll call this, we'll call this. So whenever we know what to remove, we'll just basically remove that element, compress the array, and that's it. So we don't have this chain dependency of hooks. And going to the general removal of modules, there is this d'init function that is deinitialized in every particular backend, and it does all the sort of shutting down procedures that it needs to do, like unregistered things, or, for example, OmniHTTPD will shut down the listener, right, the background worker that is responsible for running the networking components there. It'll just shut down things, and it.
That's what I was meaning, because if you load a new version of that, then one of them will shut it down and the other will start it up again.
Yes, and so we managed this. So again, a good example is OmniHTTPD. We managed to get it right that when you're updating OmniHTTPD, it will quickly terminate the background workers of the old version, and then start the new ones all in the same transaction. As you update, not even just transaction, the same command, the alter extension update. It will basically shut down one and start the other one.
You are not trying to kind of pass them over from one to the other.
Right now, no, but that's actually a hope that eventually we can do things like pass sockets between, so you don't have to close connections, whatnot. But it is a larger problem. It's a solvable problem, but it requires a lot more time commitment to be able to pass some data, some state, like sockets or any other data. It's more of a longer-term hope and dream. But right now, what we have solves our immediate problems. So kind of had to prioritize, what we do. Any other questions? So the question is how do we deal with the fact when we're updating a module, the native module, and the function name is the same, but say return type is different, or arguments are different, something is different about it. So basically the way we deal, we only change the functions that are the same. So basically whenever you do create or replace, that's a different function. Like I'll have to double check how exactly we implement it. I don't remember right now, but the general idea is what we want to carry over is things that did not change. So basically things that in your mind you never changed them, the only thing that changed about them is the location of the function, right? So when you update your application, functions may have not changed. You just compiled the new binary. The implementation may have changed, but the shape of them has not changed. So these are the functions that we do not want to change in PGProc. Because basically the expectation, if you're changing them, you are going to call create function or like drop function this, create function that if you want to remove the old one and create a new one, that's going to be a new record. That's the one we're not touching. And one of the reasons why we're not touching it is when you do that create function for the new one, it will actually get the proper reference to the new file. It's not going to be pointed to the old file. So that's kind of the main thing. Because every time you're upgrading, and Postgres does the substitution of the module path name in your script, it will give you already the new version of the file. So they're already there and we're not changing them. We're only looking at the past ones that have not sort of been moved over. And if you drop them, well, then they're dropped, we're not seeing them. So we're only carrying over the ones that haven't changed shape-wise, but still pointing to the old version, which is clearly problematic. Does it make sense?
Yeah.
Perfect. Any other questions? We were also, a little bit over time, I think. But any other questions? Just find me in the hallways.